Yep, I'm just waiting for the video feed to come up. Don't worry, we'll start soon. Perhaps you can hear us. And this is just getting the video to work. I can tell when I'm on the video feed because I'll be able to see it inside there. So I can tell that right now I'm not in the video feed yet. Oh, okay. A message, I'll just say something to our tech support group. I think that what that is sometimes that you have to just, I did the display capture that's being chosen, and then it'll come across. No video. We don't have video yet. I know we don't have video yet. We'll have video soon. Okay. We're working on it.
Ice cream, cake, salad. Wow.
Cake could be dangerous. I think it would ruin cake for me. Is the issue.
Mm. Yeah, I think you can definitely get sick of cake after eating too much.
Absolutely. Oh, burgers. I can get behind that. I love burgers. Without chickens. All right. Gelato. All right. Well, without further ado, I think we do got to get started if you guys are all comfortable with the chat. So we'll move on to our first question here. And that is, we're going to start with question 2. What is the smallest number of ladders? Let's make this a little bigger too. The firefighter must use to reach the fire without jumping in between platforms. So if you guys cannot see, firefighter is right over there, and the fire is right over here. You guys can see the fire. Firefighter does look a little small. And I think the people are saying it's a little blurry. All right. Let me
We
try
can
and
always
help.
zoom in.
Yeah, let me try and help you guys out with that, actually.
There we go. That's a lot better.
Perhaps if I get on this side.
Is that better, guys?
Yeah, I like your idea here. Actually, let's cut out this sidebar here.
All right. Okay. Looks like we're getting a lot of answers in the chat already.
Yeah.
Ryan, do you want to go over any?
Yeah, so let's start here. I think the best way to approach this problem is think about it from not from the firefighter going towards the fire, but let's think about the fire going towards the firefighter. And we'll see that we're able to simplify this question quite a bit. We realize that the fire doesn't really have that many places to go at the beginning. Like in order to get to the fire, you must travel down this ladder over here. Oh, it's not. And then you also have to walk down here and travel down this ladder. And then once again, you only have one real option here. And that is to travel down this ladder because both ladders lead to the same point. So already we've simplified this question massively here because now we only have to think, how is the firefighter going to get from here to its from its starting point to the point over here, because that from that point there's only one real way to get to the ladder. But now we do have two options here. But I think it's, and if we go down this bottom ladder here, this one over here, we're just going to hit a dead end because remember, we cannot jump between platforms. And so we must travel up this ladder. And now this ladder obviously leads us nowhere. So we must once again travel down this ladder. And we're only left with one option here. And then this ladder here. And we've reached our firefighter. So how many ladders do we use in total here? We have, that is 1, 2, 3, 4, 5, and 6 ladders. So if you said 6 in the chat, congratulations. That is correct here. 6 ladders must be used to reach the fire without jumping between platforms. There we go. All right, I'll pass it over to Eric for problem 4 here.
All right. So problem 4 is a bit of a bigger question. So let's resize it so everything makes a bit more sense. You guys said it was blurry earlier, so I'm gonna cut off the answer choices just a little bit, but hopefully it's still legible. Okay, there we go. This is a big one. It's like basically a paragraph up here. We have soccer players standing in a circle, and they're all numbered 1 through 11. So we can see that 1 is right here, 2, 3, 4, all the way around to 11. And each player kicks the ball to the third player on the left. And we can see an example of this. 1 will pass it to 4, 4 will pass it to 7, and we can probably expect it to continue. But it tells us that this kicking pattern continues until a player has the ball for the second time. So once we reach like the same person again, then it stops. So we have to find out the number of the person who kicked the ball last. And I see a lot of you guys in the chat have already put in like a bunch of answers. So that's really good. And oh, and if you have done some of these questions, like that's perfectly fine. We just want to explore like different ways and just the overall method of solving these questions. Okay, Ryan, how do you think we should approach this kind of question? Oh, I think you might be muted.
I am. That is correct. But I am back. So when we're thinking about this type of question, until each player kicks the ball to the third player to their left, and the kicking pattern continues until someone has the ball for the second time, and the cycle is completed here. The most basic way to approach this problem is just to think about is just to pretty much draw it out initially.
Yeah, that sounds like a great idea. Let's just see where
Oh,
that leads us. So we have 1 to 4 to 7, and we're just adding 3 to the number. So 7 plus 3, that should be 10. Oh, that was a terrible line. Excuse that. 10. And then 10 goes to 1, 2, 3, so 2.
yeah. The one
2.
thing that makes the problem a little more challenging here initially is the fact that 11 does not go easily into 3. So we're not just going to return back to our starting spot. But I think if we continue on here, we still may find some sort of pattern. Because if we think about it, we're about to go through the exact same cycle, but just one spot further here. We're just starting at 2 instead of 1. But of course,
So,
if we're just offsetting by 1, we're once again not going to hit anything. We're not going to hit the same players, I mean. So we're going to end up at 5, then 8, then 11. But once again, we've run to, and we're about to offset our cycle by 2, because now we're at 3. And this keeps happening because, sorry, one moment. Just had to collect my thoughts. Yes, so the cycle is going to keep repeating. We're going to offset once again and hit the remaining players we have not touched yet. So 6, then 9, and then now and only now that we've completed this cycle 3 times, we offset back to our original starting spot, which is 1. So while we do not have a perfectly clean cycle like we would if 3 went perfectly into 11, we have a longer cycle here that emerges. Eric, what do you think about this?
yeah, I think this is just your best example of just trying it out, I guess. Because, I mean, they give you the graph. You just try it out. And you'll quickly notice, as Ryan pointed out, like the pattern of getting offset a little bit. But eventually you'll come to 9, and 9 will kick it down to 1. But 1 will have the ball twice then, so 9 should be your answer. Do you want to check it out if it's like our actual answer or not?
We should do that, absolutely.
All right.
Let's see.
Okay. Looks like it is 9.
Go.
All right. Congratulations. Let's move on to question number 6.
Lucia pays $7 for 3. I believe that should say items. The cost of each item is different and is a whole number. How much does the most expensive item cost? All right. So this question's kind of weird because it seems like we're solving for 3 unknowns, and that would be really difficult to do if we just thought about it like, because we only know really one thing, or no. Yeah, and that could seem to be very difficult. The key lies in the fact that the cost of each item is different and is a whole number here. And see, since we're only talking about $7 and 3 items, this severely limits the amount of items, the amount of possible combinations we really have here. So Eric, do you want to walk us through how exactly we would work through those combinations?
Yeah, for sure. I saw someone in the chat put in an interesting idea. It was Ryan G, and he said it's going to be the $1, $2, and $4 items. So let's just look at that answer real quick. If we have $1, $2, and $4, and this is like for each item. So they are all different. They're all whole numbers, and they sum to 7. So this is our answer. But I want to see why. So if it can't be, if it is 4, why can't it be 5 or 6? Well, let's take a look. So let's look at the last case, the biggest case. So if the most expensive item costed $6, then the least we could have would be $1. Because remember, we have to keep it under $7 total. So we only have like $1 to spare. But we need one more. And the most this can be as like a different number would just be 0. But this is not a whole number. So this would never work. So we can't have, it's impossible for us to have an item that's worth $6. So let's cross that out. What about 5 though? 5, we would do the same thing. We have a $5 item. But so that means our budget now, like the remaining amount of money, is going to be $2. And so either we have $2 and $0 as our other 2 items, but remember, 0 is not a whole number, so that can't possibly work. Or we have $1 and $1, but if you guys remember, each item is different. So we can't have 2 $1 items. So it's either 520 or 511, but both of them don't work. So we can get rid of 5 as well. We already know 4 works, and we have the answer. Ryan, do you want to go over whether or not $3 or $2 would work?
Yeah. So the easiest way to explain why these two don't work is you got to refer back to the question itself. How much does the most expensive item cost? So if we first look at 2 here, if 2 must be the most expensive item, and we also must have whole numbers, and we also must have whole number prices for all our prices, there's only one whole number that's less than 2, and it's 1. And so we'd have to have 2, 1, and 1. And this doesn't work for for multiple reasons. A, you can't have 2 1s, and B, this doesn't even add to 7. So 2 definitely can work. And a similar thing's going to go on when we try 3. We look at 3 here. Well, we know there are only 2 whole numbers that are less than 3, and they are 2 and 1. And since the numbers have to be different, the 2 other prices must be 2 and 1. And we run into a similar problem, that these just do not add up to 7. And we have no other option here. And therefore, 3 is also wrong here. And 4 is the one happy medium where we don't run into the redundancies, or we don't run into the fact that we just do not have enough. We do not have enough costs to reach our $7 requirement. And therefore, 4 is our answer here. All right. We're just rolling through these so far. So let's head towards, once we confirm that we have the answer, and yes, it is $4. Let's head towards this. Question number 8. Alex has a kangaroo poster on his kitchen wall. The tiles on the wall form a regular pattern. How many gray tiles are there behind the poster?
This is an
Now,
interesting question, I
yeah,
must say.
I'd like to draw you guys' attention to gray tiles, because I know one of you just glazed over that last final sentence and was going to try and solve for the entire number of tiles that are there. But I do think that is a great way to start off this question. Oh, we have some answer choices cut off as well. There we go. So, how many tiles are behind this poster? Well, this is a pretty simple area calculation. All we have to do is count the number of tiles. We have to count the length and width of the poster in tiles and get our total number of tiles. So we have, to start with the width, we have 1, 2, 3, 4, 5, 6, and 7 tiles across. And then we have 1, 2, 3, 4, 5, 6 tiles down. So, if my math is correct, and it is, there are 6 times 7 equals 42 tiles under this kangaroo poster on this kitchen wall. So, however, that's not the question here. The question is how many gray tiles. So, Eric, how can we figure out which tiles are black and which tiles are gray?
Yeah, so also I should make a quick note of this, but since you can't really tell like where like the other tiles are, since like we have like, I don't know, a filter here, the ones that you can see are gray and the ones that you can't see are going to be black. So just treat them as black for now, or you could say like, oh, they're transparent. But regardless, so we have 42 total tiles as Ryan showed you, but how can we use that? Well, I want to direct your attention to this rows here. Notice we have 6 rows and we have like 1 gray, 1 black, 1 gray, 1 black, 1 gray, 1 black. So there's going to be an equal amount of grays per black per row, right? So if we, the best way to think about this, in my opinion, would be to like pair them up. And so what do I mean by this? Well, we can pair these two, we can pair these two, and we can pair these two. Do you see these? We can pair a black with a gray and do this for every like row, or no, this is a row, this is a column. For each column we have. So if we have 7 columns and we have 3 pairs, then we have 21 total pairs. So if we have 21 pairs, then out of each pair, there's going to be 1 gray tile. So that must mean we have 21 gray tiles. What do you think, Ryan?
Absolutely. Yeah, this is perfect. And I think that goes along quite nicely with our intuition that it looks like the tiles alternate, and thus half of them are gray, half of them are black. It's a nice, pretty way to solve this question. But yeah, absolutely. Great job with the pairing solution, but we must move on if no one has any objections. So, and there's our answer, 21. So here we go. There are 5 kinds of fruit in a bowl. Anne likes And these are 5 different people, and they all like different fruits. I'm not going to read them out for the sake of time. And it looks like we're missing the question here. But the question here, yeah, what is going on here? But the idea here is that everyone is given one type of fruit, one distinct type of fruit. And they're all given a fruit they like. So let's write this out. Everyone gets one distinct when I say distinct, I mean distinct from the fruits everyone else gets. One distinct type.
Oh, looks like it might be a bit blurry. So let
Ooh.
me show you guys what's really happening. I think the best way to do this is just writing over it. So as Ryan mentioned, we're having 5 different kinds of fruit, and the idea of the question, I know it got cut off, but bear with it, is if everyone gets the fruit they like, what fruit does Ben get? And so the first row goes to Anne. So I'm gonna put an A there. I hope that's more legible. And then the second person is Ben, and then we have Cam or C, and then Dan, or I'm going to say D, and Eli for E. So I hope that uh, gives some clarity to this slide situation. But we're given that A likes this grape, B, Ben likes all these things, C likes all these things, and so on. So if everyone gets a fruit they like, how can we find the solution to what fruit Ben like or what fruit Ben gets, Ryan?
Yeah, so what we observe here is that Ben likes every single type of fruit. He's my type of guy. I love fruit. But what's interesting, if we look at the fruits that everyone else likes, you'll notice an absence of one fruit in everyone else. You'll notice that none of them like apples except Ben. Now, what does that tell us? Since we know there are 5 different types of fruit, and there are 5 people that are all getting distinct fruits, we know that every single fruit type must be assigned a person. However, they're all assigned fruits they like. And since no one likes apples except Ben, and apples must be chosen, and apples must be given to somebody, they must be given to Ben. So we know that Ben must be given the apple, which is, if I shift over here, indeed an answer choice. So our answer here is A. Ben gets an apple. Eric, do you have anything to add on this question?
I mean, I think that was a pretty good solution. But I did see an alternative way some of you guys hinted at in the chat, which was we could just go the opposite way. Instead of going with who has the most possible like preferences for fruit, we can go find the person with the least amount of preferences for fruit. So that's Anne. Anne only likes grapes. She's a very picky eater, but we don't judge her. So if Anne only likes grapes, what can we tell? We can tell that Dan must like bananas. Why? Because Dan only likes grapes and bananas, but grapes are already taken by Anne, so Dan must have the banana. And we continue this process with Cam, Eli, and so on to find out that the only one left over, as Ryan mentioned, is the apple. And so that's going to be the fruit Ben gets. But enough with fruits. I think it's time to move on. But I think we can check our answer too. How about that? Okay. Looks like our answer is indeed A, the apple. Let's move on. Ryan, do you want to start this one?
Sure. Can I just get a confirmation you guys can read this one here? Just because I know there has been some issues with blurring the slides. All right, I'm getting some kind of, so I'm gonna make it a little bigger here. All right. Now it's kind of taking up half my screen, so hope you can read it now. Oh, it is a little cut off. That is true. There we go. All right. Peter the penguin goes fishing every day and brings back 9 fish for his 2 chicks. Each day he gives 5 fish to the first chick he sees and 4 fish to the second chick. The chicks eat all the fish they get. Over the last few days, one chick ate 26 fish. How many fish did the other chick eat during those days? And we have these answer choices. So, I think the most interesting, first we have to think about, okay, how are we actually going to get the number of fish the other chick ate? And this seems kind of trivial initially. But what I want to make clear is that the way we're going to do this is we're going to take the total and subtract 26 from it to get the other chick. Now, what we got to realize here, or what we could think about is, actually, I think better way to write this out here is total is 26 plus the other chick. And if I just drag this back over here, you guys can see it. There. All right. Now, the reason this is interesting here is because we also know something about the total. We know the total must be a multiple of 9, because every time Peter the penguin brings back 9 fish to his 2 chicks, the total amount must be a multiple of 9. So 26 plus the other chick must be a multiple of 9. So, Eric, can you take us through how that fact could get us closer to our answer here? Maybe eliminate some choices for us?
Yeah, we can look at this equation here. I know Ryan wrote it the different way with the 26 on the other side, but it's the same equation. And we know this total must be a multiple of 9 since, he gets 9 fish per day. So if this is going to be like 9, let's say 9n or something, so this is going to be like 9n minus 26 equals like the other chick's fish. But I think the 26 is pretty meaningful. And so if the chick can only get 4 or 5 a day, then some combination of 4s and 5s must be 26. And they have to be integer combinations as well, because you can't get like a fraction number of fish. Well, I guess you could, but we're assuming that the chicks only like whole fish. They don't like half fish or anything like that. So what we can do is, I noticed someone, I think it was Ryan G, put it in the chat. We can do, I'm going to move this down so I have more scratch paper. But what we can do is set this 26 equals to 4x plus, let's say, 5y. What's the meaning of this? Well, this is the amount of fish one chick gets. And this is like the number of days they're seen second. This is the number of days they're seen first. And so that's x and y. And we know that this must have some integer solution. And I think some of you guys noticed pretty quickly that the easiest one to see and the only one there is for this, or only one with positive integers that is 4 as x. Oh wait, let me rewrite this. 4 times 4, and then we have 5 twice. So this will be 4 times 4 plus 5 times 2, 16 plus 10, 26. Okay. Yes, and I see Hao Liu put it in the chat. We have 5 5 and 2 5s and 4 4s. So the other person is going to be like the opposite of that. We're going to have the other chick is going to have four or two fours and four fives because they have to like op how do I say this the best way? Like the two here is going to be the two here, but the four here is going to be the four there. It's a lot of fours and twos and whatever, but essentially, if the first chick that we know got was seen second four times, the other person must have been seen first four times. And same way, vice versa. So this must be the total number of ways, or the total number of fish the other chick gets. And we can calculate this out to be 8 plus 20, which I think means our answer should be 28, which I did see a lot of you guys put in the chat as well. So I think we're pretty safe there. But to be extra safe, I think we should check our answer. So let's see. Okay, it is indeed 28. Let's move on into question number 14. Unless Ryan, you had anything.
No, that was perfect. All right. Here we go. Lucas wants to make a caterpillar that has a head, a tail, and 1, 2, or 3 puzzle pieces in between. How many different caterpillars can Lucas make without flipping the pieces over? All right. So the key thing to notice here is going to be these little connecting pieces here, because they're going to define how we can actually put these pieces together. So what we know we have to include is this head and this tail, right? But that places some restrictions on what connectors we can actually use at any point, because we know that the last connector must be one of these holes, because it's got to connect into that connector. And we know the first connector must be one of these holes, because that hole must connect into this connector here. So that's going to severely limit the number of different pieces we could actually put together. So to begin here, if we have the head here, we know we have the head, and we start off with the head. We know there are only two possible combinations. There are only two possibilities for puzzle pieces we can put directly after the head, and they are this one and that one. And we can continue that process, as Eric will, to get our full number of combinations we can use without flipping the pieces over. So Eric, do you want to finish this off here and finish this problem off?
Yeah, I'd be happy to. So Ryan already laid out pretty much the framework and everything we really need to know to solve this question. He noticed that the first like hole here can only be fit by the heads of these two like connecting pieces. Oh yeah, and by the way, the head and the tail have to stay where they are because you can't have like your head in the middle of your body. That wouldn't make sense. So we have to have the middle three switch. But Ryan noted that the the hole here only fits for the head of these two. So for the first person, we have two options for like the first position after the head. And it's going to be one of these two. But it actually matters which one it is because if you notice the like connecting tail at the end of the connecting head or connecting piece is different. Like we have like a rectangle one here and we have like an oval one here. So let's pretend we have the cherry first. So we have like uh, the cherry here. I'm just going to draw lines. If the cherry goes here, we need to have a square or a rectangle connector. And the only one we can do is this one. So that means the green apple is forced to be here. And then if the green apple is forced to be here, then we must have this tail because, well, this wouldn't fit because it's like an oval connector in the rectangle connector. So that just wouldn't work. So we need like the head there. So this works. This is one way. Ryan, are there any other ways?
Yes, so we do start with this. Yeah. So Eric first points out this way of where we use the cherry, then we use the green apple, and then we use a banana here. But beyond that, let's stick with the cherry here. Oh, wait. So we have a way where we have the head. I'm going to abbreviate these actually. Yes. Head, then cherry, then the green apple, then the tail. But we can also just remove the green apple because, as we can see, the cherry back and the tail are compatible. So we have head, cherry, and tail. But then, even beyond that, we can change up our initial puzzle piece here. So instead of using the cherry, we can just use the grape. But now we can no longer connect the tail in because the tail has a different connector piece to this that isn't compatible with this hole. So we've got to throw the cherry on. But as we know, the cherry connects to the tail. But what we also know is that the green, oh, this abbreviation method does not work because there's two G's. There's a green apple and a grape. So we're going to call this an apple. There we go. Yes, so, but we also know is we can attach the cherry onto the apple, and the apple also connects into the tail. So we can have head, grape, cherry, and then the apple on the back of that. And then we know, since those endings are compatible, we have the tail at the end. But from there, we've exhausted both of our possibilities for the first puzzle piece, and therefore we've come to our answer of 4 here. And unless Eric has something to add.
Not really. I mean, that was pretty neat. So, I mean, let's just check our answer then. I think it should be 4.
Yeah. Let's see. There we go, 4. But we can move on to problem 16 here. This one looks like a doozy.
All right. So,
Yep.
we're given a floor with 2 kinds of tiles. And these are like the black ones, I guess. You can't really see it, but I guess you kind of can because it has like the imprint of it. But we also have these like grayer ones. And so these are like the small gray ones. And I realized that now looking at it, kind of looks like a pie and it's making me hungry. But we shouldn't worry about that right now. The size of the rectangle is 23 centimeters by 11 centimeters. So this is obviously the longer side. So let's write that down. The longer side is going to be 23 and the shorter side is 11. Okay, so 11 and 23. The picture shows a part of the floor, and we're trying to figure out how long is one side of the square tile. So that's going to be like this gray thing we have. Well, I think the first way to approach this is just going to be looking at what we know from the picture. Like, what does it tell us? Does anyone have any suggestions? Because, I mean, we don't know how long or tall these are. I mean,
Wait,
we know
Eric,
this is a square.
I believe the size of the rectangular tiles are 23 by 11.
Oh,
Picture itself.
I
That's it.
see. Wow. That does make things a lot easier. So we are given the length of the rectangles. So, and we are given the height of the rectangles. So let me remove this real quick. So we know 11 and 23 like this. That's really small. Thanks for catching that. Can we do anything to find what, you know, the length of this super small thing is? Huh. Ryan, why don't we take a look at perhaps one of these like lengths here? Let me draw it out, or let me circle it for you. Like, because we have a square length, and like the short side, and that's going to be equal to the long side of this rectangle. What does that give us? Do you happen to know?
I'm just going to blow it up over here. What you have with the setup in the picture, because this should be the key to what we're defining the size of this rectangle, of the square tile here. So what do we know here? We know our side, we know our rectangle side. So we know this entire side is 23 centimeters. And we know this shorter side here is 11 centimeters. So we've somehow got to find a way to make up this 12 centimeters, these 12 centimeters between remaining that is not covered by this 11 centimeter length here between two square blocks. And how can we do that? Well, we can just divide 12 by 2. And that'll be our side length because as we can see, that 12 centimeters is covered by 2 side lengths. So with that, we divide 12 by 2 and we get 6 centimeters, which ends up being our final answer here. So, but we should still check our answer here. So let's see if it's correct. There we go, 6 centimeters. So let us move on to question number 18. And it's a diagram problem, so I'm going to expand for you guys. There we go. Oh, that's a little too big. There we go. Excuse me. Lucy weighs some blocks. And as you can see, this one is 200 grams, 100 grams, 240 grams, and we do not know this mass over here. Oh, actually, there is crucial information that's taken off there. And all these different polygons and the circle all have different masses here, which we are not given. We must find out how much do the 3 different blocks weigh together. So where to start here? So we have all 3 of these masses. Or no, we do not have all 3 of these masses. We just have the way the masses go together. And I think one interesting thing we can notice here is that if we add together all of these masses that we know here, we're just going to get 2 times the mass of this right here. Because, as you can see, there are 2 triangles, there are 2 rectangles, and there are 2 circles. So that's just this mass twice. But we have the value of these 3 masses added together. That's just 200. Oh, I'll call off my screen. There we go. Plus 100 plus 240, which of course equals, I almost said 440, 540. All right. And since we know that is twice the mass we're trying to find, we can simply divide that by 2 and get 270. Once again, off my screen, which will end up being our answer here. So we're just blazing through these. But Eric, do you have anything else to add on this question here?
Not really. I mean, just the main idea of this question, as Ryan mentioned, was noticing that if we just added these three together, we would have a scale with two rectangles, two triangles, two circles, and that's exactly double of what we want. So the answer extraction is pretty easy from there. Let's check our answer and move on. Okay, it is indeed 270. So congratulations to anyone who got that. But for now, let's move on to question number 20. Huh, more shapes. Let me position this better. All right. In the following calculations, the same digits are hidden under the same figures. Okay, so what that just means is like this triangle has the same value as this triangle, and all the triangles are going to be the same, all the circles are going to be the same, and all the squares are going to be the same. And the different digits are hidden under different figures. So, I mean, they're not going to be all the same. And we're trying to find what is the value of the triangle times the circle times the square. So, I think we should assign some variables to this. Um, let's use some, I don't want to use like T for triangle because that kind of looks like a plus sign. S and O would look weird because that kind of looks like a zero. So instead, what I'm going to do is I'm going to say that the triangle has a value of A, and I'm going to say the square has a value of B, and the circle C. So we can like basically change our equations into a bunch of A, B's, and C's, and that might help us because right now, I mean, you can't really multiply shapes together. If you could, that would be really cool, but I don't think we could do that yet. So let's convert everything. So we have A plus A equals BC, C plus A equals BB. I'm gonna assume this is multiplication because there's no like there's no sign here. There's no like
Eric,
plus sign or whatever.
Eric, I would believe they're digits. So I think this is a two-digit number here.
Yeah, okay, that makes sense.
So I don't
So,
think it would be multiplication just because they have the signs here.
I see. But in any case,
Sorry to be that
we
guy
can
again.
still make this useful because this is just going to be 10b plus b because we have like a tens digit and we have like the ones digit. So this would be 10 times b and this would be 1 times b. So let's figure this out first. If we're going to convert the first equation, that's going to be 2a equals 10b plus c. And our second equation is going to give us C plus A, or let's write A plus C equals 11B because we have 10 plus 1. Huh. How can we solve this equation knowing that these are like digits, Ryan?
All right. Yeah. The one really interesting thing you can notice here that makes this a whole lot simpler to solve here is that we know that these and all these values must be one digit integers, positive integers too. So what we can observe here is that B here must be one. Oh, B here must be one because if it was two, this or anything larger, this number would be something like 22. And there's no way to add two one-digit positive integers to get 22. Because think that the highest you can go is 9 plus 9, and that only gets you to 18. So this here must be, oh, one moment, must be 11. And that makes our equation a whole lot simpler here, because this just becomes, we can pretty much just erase B. So this becomes 2A equals 10 plus C, and then A plus C equals 11. And this system is a whole lot less daunting because now we're solving two equations with two variables here. So what would we do with this system here? We
Well,
would,
I
oh
think
yeah,
the easiest way here is we have these two equations, right? From Ryan's like analysis of B. So we know B must be 1. But if we notice we have 2a and a plus c on like the left-hand side, and we have a 10 and a c and an 11. So what if we just added everything on both sides together? We would have 3a because 2a plus 1a, that's 3a. And we have c, so c here. And so that's going to be our new left-hand side. On the right-hand side, we have 10 plus c plus 11. That's going to be 21 plus c. Notice something interesting here. We have a C and a C on both sides. That means we can get rid of them. That's really nice because we can subtract C from both sides. So if we just get rid of the C's, we have 3A equals 21. And I think that just means A must be 7. And if we plug this back in to this equation, it doesn't really matter which equation actually, but just this equation for actually let's do a plus c. So a plus c is 11, and we know a is 7, so c must be 4. All right, I think we have all our values now. What does that make the final answer, Ryan?
all right. So it's going to end up being, we just need to multiply all these different numbers together. So it's going to be 7 times 1 times 4, which is just going to get us 28. And with that, once we make sure our answer is correct, of course, and it is 28, is going to wrap up our live solve. So great job, everybody. For following along. Thank you for listening to me and Eric and being such a great audience. I hope you learned something because it's always a pleasure for me to work with you guys.
Yeah, thank you guys so much. This was really fun. And you guys were always putting stuff in the chat. So that's great.
Yeah, it's always great to see. All right. Thank you guys. Keep doing math. We'll see you around. And yeah, bye everyone.
All right. Bye, everyone.